development of laser-based additive manufacturing systems and the processes. And I'll start my talk with a quote from Dr. Homi Bhabha. He told very clearly that if Indian industries is to take off and be capable of independent flight, it must be powered by the science and technology base in the country. So that is the way. And then at our Department of Atomic Energy, we did a lot of things in this direction and worked on this. If you talk of my team at RRCAT, we have pretty balanced team. We have around 17 employees who have on the role, and then we have pretty large number of the students community. So all are working in this and making the things differently and trying to work on whatever they want to.
Recording in progress.
So before I start, let me tell about what RRCAT is. RRCAT is Raja Ramanna Center for Advanced Technology. It is premium R&D unit under Department of Atomic Energy, Government of India, engaged in non-nuclear frontline research areas like lasers, particle accelerator, and related technology. This is also Constant Institute of Homi Bhabha National Institute, deemed to be University under Department of Atomic Energy. So this is the thing. And then again, just for the information for you all guys, that in university category, the HBNI is ranked as 16th in the country in the recent NRI ranking. If you talk of the activities at RRCAT, we are working on the particle accelerators and the lasers, and we have in the particle accelerator we have electron accelerators 450 MeV and 2.5 GeV synchrotron radiation sources. We are also having electron linacs and the proton accelerators, and we are using these for various industrial and medical applications. If you talk of the lasers, we have all type of the lasers, irrespective of the type. If you talk of any applications in the field of lasers and optics, you will have at least one scientist working in this domain. So this is this. And to develop these technologies, we have done expertise into various associated domains like RF and microwave, cryogenics, optics, magnets, instrumentation control, precision power supplies, ultra-high vacuum, advanced manufacturing, and material processing. So a lot of things we have done in this. And recently we have started one incubation center, AIC Pi Hub. This is a Section 8 company with the 100% equity holding by Department of Atomic Energy, and it is supported by Niti Aayog Atal Innovation Mission. One thing comes for us, why do we need to go for research and development? I'll just start with a very basic thing. This indigenous development is required to signify the self-sufficiency and independent growth of additive manufacturing capability, which is powered by the local research, development, and innovations. If we just depend on foreign technologies, equipment, and expertise, probably the innovative mindset that we have will slowly die down and it will not be useful, right? So it is important that we need to develop these technologies in-house so that we can foster domestic capabilities to meet the specific requirement. For example, if I talk of the Department of Atomic Energy, so we are doing a lot of things in which probably recipe will not be available as in the standard machines which are available from other sources. So this is the requirement, and therefore we have taken a comprehensive program for the system and process development with the requisite structure so that we can make and meet the requirement that we have for the development of indigenous technology in the field of additive manufacturing. So we started long back, and in 2003, we started the work in the field with my PhD on additive manufacturing, and probably this was the first PhD in the country in the laser-based additive manufacturing using direct energy deposition. And you see on the right-hand side, we have a CO2 laser-based LAMP system, a DD system that we developed that time. And then after that, we moved to 2 kilowatt fiber laser-based systems in 2013. And then powder bed fusion system, we developed 500 watt with open modes in 2018. 21, we start supplying the machines to BRC, and then 23, we started the commercial launch of these machines in Indian market. So this is the journey that how we started, and now it's whatever I'm talking to present to you. It is just glimpses of what we did in last 22 years, and it's not the day, and it's the sweat of the all my team members. The members name that I have written, they are the current members, but many people contributed in the superannuated, and many students who are now alumni to us, they contributed significantly in the development of this technology in the country. You know that we have two type of additive manufacturing systems. One is called direct energy deposition, another is powder bed fusion. And whenever we talk of the direct energy deposition, means we are using laser and jet powder jets. And then you see on the left hand side one picture is there. Then what we are doing is we are trying to in situ melt these metal powders and deposit and give the shape whatever we want. And the basic advantage of this particular technology is that we can make functionally graded structures. We can think of multi-material components. The shape can be the near net shaped components, and then complex geometries can be tried out. But if we talk of the powder bed fusion, which is very common into the market today, like we have many players, EOS is there, and then SLM is there. Now in Indian terms, we have now Intec DMLS, and then we have now Amaze. So we have Indian machines also available for the laser-based powder bed fusion machines. In this, what we do is we simply lay a thin layer of the powder and selectively melt the powder bed using lasers. Cases, you can go for unlimited complexities. Since the thin layer is there, then you have very very massive structure, which is working as a sink for the heated metal powder. So we get very refined microstructures. And since we are able to make porous structures and many things, it's possible to build lightweight structures, and thin features fabrication is possible. When I'm talking of making the thin features, means you can have a structures as thin as few hundreds of micron. We could make up to 250 micron very nicely, and these structures can be used in various application. Otherwise, not possible to go ahead with. So this is a machine that we did develop, that powder bed fusion machine, and we have tried many materials on this. We deposited SS316L, then 304L, Inconel 625, Inconel 71, titanium 64. Copper is tried out, Astrolax, and then copper chromium zircaloy and copper niobium. So we all these tried, and this is basically 500-watt fiber laser based system. Presently, the machine that you are seeing is having a beam diameter about 500 micron. So that simply means that you can have feature not smaller than 500 micron, and the build volume it is having about 300 into 300 by 300 millimeter cube. So this is the machine, and just for the information to the people, that we have already supplying 2 machines to BARC, and we have asked for the expression of interest for the incubation of these machines now. Will be available in the next week. The things are ready now anytime. So people who are interested to take the technology and develop and build these machines by our own can be connected with this, and the technology can be taken to the next level. So this is the shape, so that some of the components that we built using laser powder bed fusion system. If we talk of the thing that which is at the center with the white background, you see in the CAD model we have some internal and external part with the helical cooling channels, which is very difficult to make in conventional technology, and this can be used for making some specific molds and dies. So what can we do is, you can think of doing some analysis of some mold and cavity design, and based on that you can find out what is the optimum cooling channels and how things can be done, and then these machines can build it for you, and that is the thing. Similarly, if you talk of the developing some graded features, you have something here on the left hand side, the middle one, that is with a yellow background. So here the graded features are there in this. And if you talk of the bottom side, we have some compressor blade. This is also built. So it is possible to build very complex and structures without having structures. Yes, surface finish is in the range of 5 to 25 micron, depending on the components that we build. But if the feature is very complex and things are to be done, then it is a right solution to proceed ahead. I'll be sharing some of the examples in the later part of my presentations, where we'll be talking more in detail about.
ஹெல்மெட்டுக்குள்ள போட்டு
Similarly, we have developed in-house directed energy deposition machine, and one machine we are already extending into BRC, and then we have given this technology to the 3 industries. It is 2 kilowatt fiber laser based machine with the 5-6 workstation, having a volume of 400 millimeter by 400 millimeter by 300 millimeters. It has got 2 powder feeder, so that you can use 2 metal powders simultaneously, change their compositions and work on it. The feed rate we are is having in the range of 2 to 20 gram per minute, and everything is in a glow box, which is having purity level by continuous purging can be achieved less than 20 ppm of oxygen and less than 30 ppm of moisture. So this can be done. We have developed many materials of our requirement. For example, SS316L, 625, 718, Deloro 50, columnite 6, Hesterstellite, Titanium 64. Many materials we have tried, and the team has expertise now. They can develop many applications for this. Recently, we received one more requirement from our sister concern, and then what they want to have graphite deposited on some nickel-based alloy, and the thickness of graphite they wanted to be in the range of 200 to 250 micron, and depositing graphite using any other means on a metal surface is really tricky. So we have some limited success in this, and then we are trying to make it this, and specifically these things will be used for highly corrosive environment. So something better will come out very soon out of this. If we talk of the DED components, we have built many components. You see the pictures I'm showing you, Deloro 50, silicon clad layers, copper nickel alternate layers. This is a beauty. Like you can have a 50 alternate layers of copper and nickel, and each layer is of 500 microns, and these things can be used for thermoelectric generator TEG applications, which is not possible otherwise. You can't have all these things built together and made it. Similarly, moly clad layers on copper chromium zircaloy is done. SS titanium transition joint is built, and we also built on the making micro channel heat exchanger that you are seeing on the right bottom corner of this. And this channel is about 2 millimeter by 3 millimeter channels, rectangular channels across the job. And the job size that you are seeing is about 250 millimeter by 250 millimeter by 250 millimeter. So you have a cube. And again, it took a long time for us to build. Now it looks simple, but if you start depositing this, and the typical deposition rate we get in the range of 6 to 8 or maybe 10 gram per minute, and you have to deposit, say for example, maybe 50 kg, then you can understand how much time we take to build such a big volume. But it is doable, and we are doing a lot of things in this direction. The technology that whatever we developed was incubated, and we signed agreement with 3 companies. Unnati 5D Manufacturing Systems Private Limited, Mumbai, it's a startup. Another company is Fuse Metal for Manufacturing, Bhopal, it's also a startup. And also CNC Giant Lokesh Machines Limited. And these 3 systems are incubated with us. This machine was developed by Lokesh Machines Limited, and it is launched in Amtech show in 2023 at Hyderabad, December 2023, and then now the commercial production of this machine is starting very soon. Another thing that Fuse Metal Manufacturing is also made the machines. Now this is also launched on 4 September 2024 during our anniversary of the AIC Pi Hub. So this also was a wonderful work that is done, and now these 2 machines are are well into the market. What I want to emphasize on the development of these machines brought a lot of things into the country. We developed these for our lab requirement, and later the industry took it up and then they started making it. The typical cost of these machines by location refuse will be in the range of 2.5 to 3.5 CR. And if you see this and you buy it from some other sources, for example, you buy from other UK or US machines, they may be costing in the range of 5 to 7.5 crore. So again, developing this technology brought a different game, and now we are also trying to bring the cost further down and trying to make the machine more complex. But again, what we did in its whole strategy is we use standard modules to build the machine so that uh, it is commercially viable. If there is some problem with the machine, you have experts available in the commercial market. For example, the controller it has is from Siemens, Mitsubishi, or Fanuc, which is a very standard controller for vertical machine centers. So like that, we are trying to work on it and making things into a different domain, which is making very attractive for India to proceed ahead with the technologies of laser additive manufacturing. We are also trying to incubate many other technologies. For example, whatever the technologies I talk about, always the based on the powder-based lamp systems. We are also co-developing wire-based nozzles, some softwares for lamp PBF, because today people are using either some companies named the Materialize from Belgium, the very costly softwares, and then we are trying to come up with some low-cost lamp PBF systems. So many more things are under pipeline so that these developments take the country. And again, I am just having a some thing that in my mind when I'm talking about low-cost lamp PBF system, that if you have a machine built, a powder bed fusion machine, maybe very small in build volume, maybe say 100 by 100 by 150 or something like that, or maybe 120 by 120 by this, and if the cost can be less than 40 or 45 lakhs, so probably it will be viable for every engineering suit, or maybe whatever the one in a, get the funding for machines. Today, the cost of these machines are in the crores, so which is not possible for engineering institutes to apply for. But the low-cost machines we are trying to build, and if it is built, definitely is going to be the game changer in whole technologies. One such machines we built, you see the small one. This is for the demo. This is a portable lamp PBF machine that we did built. If you talk of the size of this machine is around 4 feet width, 4 feet depth, and around 1.2 meter height. So this makes the very attractive proposition. We unveiled this machine on the September 4th, and it's really making a big difference into this. We are now showing this machine to the different exhibitions to have awareness about the technology, and we are going to work ahead with this. We are also organizing many innovation challenge in the field of additive manufacturing. For example, we ran a competitions on novel concepts for low-cost based metal 3D printers. So all these things are done, and many success stories are there with us. Not only stopping to the commercialization of the technology that we have developed, we are also extending our efforts to make the some to different thing which is not trivial. For example, material deposition on the vertical surface is one of the challenges. For example, you want to have some elbows or bends where the material erosion is very high. Can we have a deposition head built using laser technology? It goes inside and deposits the material. So such a laser head is developed, and you can see on the left hand side of the slide that today we have this machine which can build the material anything which is less than 45 micron in the size. Another thing is that we are trying to expand the size of the part, for example, from 400, maybe 400 by 400. We are taking it to next level, going to the larger volume for the 1.6 meter and 1.4 meter length. The one machine is already built in this direction, and then it is again robo-based, and then again trying to resolve the challenges how to integrate the 3D model transfer to the robo. But again, this machine is shown viability, and some initial trials are done, and it's good. And then again, what we are targeting, if these such machines are built, then this can be used to build very large size component. For example, you want to make a say rocket thrust chambers, which may be in the size of meters, so that such a large component can be built in using these technologies, and different design can be tried out. And this will also provide opportunity for the designers to have features into these high-end components, which are not possible otherwise to build using conventional technology. So what are we planning is, we are not going to stop here with the laser-based systems. We want to go ahead further to make electron beam-based additive manufacturing. We are also trying to work on twin wire arc-assisted additive manufacturing. We are also trying to couple multi-lasers, multi-material additive manufacturing using powder bed friction technologies, so that things can be done, and also trying to take up some of the assignment in the range of ultrasonic friction stir or binder jetting systems. Again, these are the future steps that we are planning to have. Definitely, we are trying to build the process windows for the metal, ceramics, and ceramides, so things can be taken. Again, we are working on many post-processing technologies like laser pinning and laser polishing, so that the machine and the technology becomes very cool and becomes. So this looks fantastic, and this is the journey that I talked about. What our near future plan also I shared with you, so that you have a fair idea how RRCAT and the team here at Additive Manufacturing Technology Lab is making the difference in the country and contributing to Atmanirbhar Bharat, and contributing the Viksit Bharat mission. So now I'll be talking about the applications that we have developed. We have a pretty large collaborations. Number list of the collaborations really big. Uh, all the big institutes, you talk of BRC, IGCAR, Institute of Plasma Research, ARCI, or Vikram Sarabhai Space Center, LPSC is also joined. And all the good institutes, in the country, for example, IIT Indore, Kanpur, Bombay, Guwahati, Palakkad, all are working with us, and many NITs, including NIT Warangal, then Suratkal, IITDM, Jabalpur. So all are working with us, and we are trying to build. And if you list the number of the institutes that are working with us, there are not one or two. There are 32 now, and people are trying to work and develop technology without any issues on that part. One of the beautiful example that I share how the laser additive manufacturing makes the difference into the domain. We have developed the 540 mesh type spacers for the fuel cluster simulators of 540 megawatt 540 megawatt electric pressurized heavy water reactor fuel bundle. You see this is the component which is shown on the left hand side at the bottom. The size of this part is about 112 millimeter, and it has got 37 holes, and the thickness of the wall that you are seeing with the circle is around 0.5 millimeter, and the tolerance requested is around 100 micron. So this is the thing. And in fuel cluster simulator, we need to have 92 such pieces which are required to build it for the experimental facility. For the thermohydraulic behavior of the reactor fuel elements is to be required, and 92 such pieces are required. Considering the type of the shapes and the requirement, one of the best way to do it is using wire EDM. And if you go with the wire EDM, then in 5 working days, we are getting almost 3 such pieces built. So if you have to make somewhere around 92 pieces, and then you have 3 pieces built in 5 days, now you can compute how many days we need to build these things. We took over this challenge and tried to build the process, and using laser powder bed fusion technology, when we deployed this, the fabrication time come down to 2.5 hours. So what I want to say that something which was somewhere more than 1.5 days is now reduced to 2.5 hours. So days has come down to hours, and once you're talking of the numbers of 92, the technology is really making the difference, and this really pushed. And once this mesh type spacer was on the critical path of the project, and if critical path is compressed, then you can understand and appreciate how whole project has changed in scenario. On the right side, I'm showing you how these spaces are split into the fuel bundle for the testing. So that is the part of things that we did, and these things are successfully implemented, and this is really good for us to talk about it. Second application is about honeycomb geometry orifices. These are made up of SS304LN and 304L. These are installed in the prototype fast breeder reactors sub-assemblies as a pressure drop devices. You are aware of that. In fast breeder reactor we have liquid sodium for heat extraction and is used. And when there is a radioactivity, then we want that the temperature distribution across the whole bundle should be uniform. And for that, what people do is you need to have unequal flow at different places, because at the center of the bundle there would be more heat generation, and at the edges it will be less. So what ideally you need is you need more sodium to flow in the middle of the core and less on the side, so that these can be done. And then these honeycomb shaped orifices are small pieces. Diameter is around 75 millimeter, and then you see the shape looks simple but very difficult to build. So these honeycomb shaped orifices are placed one after another, and by just tilting is by 15-degree, you will see two consecutive honeycomb shaped orifices. See the bars which puts the pressure drop on the path, more resistance into this, and that way the flow of the liquid sodium is controlled. So this is done, and again lot of things can be tried out using this. In the initially, I showed you a heat exchanger in a pretty large one, 250 by 250 by 250. This is again we built for our applications into the potential application into supercritical CO2 Breton cycle of solar thermal energy generations and generation for nuclear reactors. And these are required basically because these compact heat exchangers are really have compact, and since we are using supercritical CO2 gas for this, so CO2 liquid into this, so pressure drop is less, effectiveness is very high, small things are required, and this is really magnificent. Conventionally, if you make these heat exchangers using people are not using PHE technology, for example, electro etching technology, which is the material is removed by etching. Printed circuit etching technology, people use it, and again that is very slow and cumbersome process. If we talk about making this heat exchanger and the cost of it, one company from the Western Europe, if you buy, the cost of these heat exchangers can be in the range of 50 to uh, 55 lakhs each. And if you build using laser DD machine or LDD that we develop here, with putting all the expenditure, everything, the cost comes out to the 7 lakh or so. And again, the freedom to choose the design of the heat exchanger is the bonus for us in this case. So this technique successfully built, shown to the people, and then things are coming into this, and we are gearing up for making such a large component for many other applications. Another application that we had was to deposit silicon carbide on zircoli 4 tubes. And these things are, you must be aware of. We had one accident in Japan, Fukushima, because of the tsunami, and a lot of things happened. And after that, a lot of efforts are being done how to, have a reactor more safe. Though Indian reactors are already safe, but again, whenever something happens, our Atomic Energy Regulatory Board defines the more, stringent norms. And again, as a part of this is done, and we are trying to develop some accident tolerant fuel tubes and then zircaloy tubes. So what idea is, can we have silicon carbide deposited on zircaloy 4 tube? What I want to say that you have to appreciate the thickness of zircaloy tube here is 0.6 millimeter, and the silicon carbide of 0.2 millimeter you have to deposit on. And we started working on it. A lot of issues were there. There was a burning of the tube, fusing of the many things happened. And even the dilution was very high. Then what we did is we came up with very novel idea of argon flow from the inside the tube, and very effective way. This changed the whole scenario, and you see on the right hand side we have a microstructure where you are able to see the clear distinct of the silicon carbide clad deposit and then zircaloy 4. And if you see that really we could achieve 200 micron of silicon carbide and then the 400 500 micron of zircaloy 4. So this made a very open and new avenues where things are changing the overall game, and we are able to make accent tolerant zircaloy tube fuel bundle with this, and this technology will be really attractive in future to move ahead with. Whenever we talk of laser direct energy deposition, probably one of the things that normally come to in our mind is, can we make multi-material functioning gated materials? Some of the studies were tried out for us in this direction. We did the deposition of copper directly on the SS. Then we also mixed 50% of copper and SS, and this is deposited. Then we also did the grading with the 20% of change of this, and all the three samples were built, and then their properties were investigated and how things can be done. You must be appreciating this when you have a functioning graded material like you have copper and SS, where the coefficient of thermal expansion is pretty large, and then they see the temperature difference and a change of the temperature during the service. Then what is going to happen is the copper will go in its way, and then SS will go in its way. And we all know that the coefficient of thermal expansion for copper is much higher than SS, and then it puts a lot of stress at the interface, and the components are likely to fail from there. So what we are trying to do with the FGM is, we are, in spite of having a step change in the composition, we are going to have a graded composition change. For example, you see on the 20% graded copper SS bulk, we have 100% SS at the bottom. Then we are increasing 20% copper on that and 80% FSS. Likewise, and if you go to the upper, then the top layer, you have 100% copper available. So this made a very smooth transition of copper to SS, and at the interface now we have the change in the thermophysical property in the graded way, and this is definitely making a lot of difference in terms of the components can be built using this technology, which is not possible otherwise. There was a requirement from Institute of Plasma Research to build some component for ITER. India ITER, you know, that International Thermo Experimental Reactors that we are building at the France. So to have to demonstrate the laser fusion technology, nuclear fusion technology. So in one of their components, they wanted to have a 100 micron moly on the copper, and this copper is basically not nothing but copper chromium niobium alloy. And idea here is, if you have a moly on the front, and then when you have a plasma inside, the erosion of the material will be less, and that was done. Then people try to work on using PVD, physical vapor deposition. Even the CVD was tried out, but again the thickness was limited to 3 to 5 micron, and then here we are talking of something more than 100 micron, and we deposited this with one good thing that I want to tell here, that deposition of moly on copper was not possible. So what we did is, we introduced a nickel interlayer. So you have a copper, then we have deposited nickel over it, and then we have deposited moly on this, and then moly and nickels are good, and then copper nickel are good, and introducing this interlayer made our life very simple. So we built components of this, tested the properties, we did the UT of this, of the whole plates. We built a plate of 250 millimeter by 250. Now 1 meter by 1 meter, we are trying to build a very soon. This inquiry is going to come to us, and we are going to build this. So that's the way the whole thing can be done. And you see the copper chromium zircaloy molybdenum can be deposited, and once this does, the thing becomes a very different. Something similar we also tried to build in the range of the Inconel and SS. Here the application can be different. Like once you go for co-deformation, you have one vessel made up of Inconel 625, another we want some part of the SS 304, and you want to go for the co-deformation, like you want to bend it or you want to roll it. Then because of the different thermo-physical properties and the spring back effect, the things becomes very critical when you do such forming process. So here also at the interface, we try to had we try to have a gradient thing of the biometric, and you see on the right hand we have micro hardness shown how the micro hardness is changing from SS to inconel, a smooth change, and the microstructure is also visible here. So these applications are really good, and this we did for IGCAR. There was also a requirement to build deposit yttria stabilized zirconia on SS304. Successfully it is deposited for some of the applications that we have in our industry. And for one of the applications, they wanted tungsten carbide to deposit on SS30 still without any defect. So again, we did, and this application is really very challenging, and things are really changing the scenario here, just to have that tungsten carbide can also be deposited. Alumina is deposited on SS. The things were tried out. We could achieve 95 density. So that was done. We also tried to have SS titanium transition joint. Here, deposition of SS titanium direct is not possible. Then we had some interface alloys, worked on this metals, then things came up. And this is done smoothly, very nicely. This application I was talking to you in the beginning, that we had a copper and nickel alternate deposited, like you have copper, nickel, and then 50 of these of 500 thickness, 500 micron thickness. And really it's not possible to do it conventionally. So these things are done, and then these we can use it for TEG applications, and these things are again cannot. So what I want to do it, if I see whatever I talked so far, and if you think on those lines, we need to have a promising advantage if you talk of the laser additive manufacturing technologies in terms of low cost customization. Like, you can have very much customized product, which is not possible otherwise. Technology can be used for building rapid prototyping and the production parts, which is going to make a difference, and the faster adoption of the new ideas are possible. We can also use this technology to generate gradient with more complex 3D composition and phase and grain size modulations, which is now talk of the day, and people are doing a lot of research into this direction. And specifically, these technologies can be used for the performance enhancement of the existing components, like I talked of the radiation swelling, or maybe more accident tolerant fuel bundle, like we have deposited silicon carbide on zircon. So this is making a lot of difference. And similarly, if you want to have energy consumption reduction, so a lot of things can be done. So we have a lot of potentials, and since we are working in the Department of Atomic Energy, we were primarily focused on developing components for the nuclear applications. Nevertheless, when I'm talking of these things, I'm also talking of the materials, so that you have a fair idea of which are the materials can be used and how the technology can be taken to the next level. There are many success stories about it. For example, in one of the cases that we working with one of the companies with us, they are working with the defense, and now defense for one of the tanks that we imported from Russia. The cost of the one gearbox is around 52 lakhs, and it has got 11 gears in that, and only 4 gears wears out, not all the 11. And the Russian don't sell to us, the spare gears. They sell whole block, the whole gearbox. So what our people did is they tried, the industry came to us, they started trying to build some of the components using this technology. And finally, we did some of the material research, try to find out which material they are using, and how we can have this material built and developed in the country, and how this can be used for making the gears. After having successful these trials, after making such gears, these were given to armed forces for the testing, and these were tested for 32 hours successfully. Once we developed this technology, and after maybe 2 weeks or so, the head office of the armed forces received a letter from Russia saying that now, considering the long-term association with us, they are ready to, supply the spare gear in a cost around 8 lakhs each. So if 4 gears goes bad, and then the cost, if you see, it comes out to be around 32 lakhs. The things which was earlier given in a 52 lakhs now has come down to 32 lakhs. Moreover, our technology is giving the cost of these gears in 1.25 lakhs. So if you go with the 4, then 5 lakhs. So where is 5 lakhs? Where is the 52 lakhs? The whole economics change, and this is one of the example that I'm talking of. But there may be many examples where laser additive manufacturing is making the difference by just changing and giving the solution in different type. So if I talk of our experience that which we have done, whole portfolio of laser additive manufacturing can be divided into the 9 domain. One is like machine and software development. Second is process development and control. Material and the feedstock development, design for laser additive manufacturing. Modeling and simulations, characterization and testing. Quality control and assurance, development of the applications, and the most important, education and training. Yeah, out of these 9 volumes that we're talking of, we have a good presence in the field of all the 4, which is like machine and software development, process development and control, characterization, testing, education, and training. We do not have much presence in the case of materials, feedstock development, and the quality assurance and the control. We are doing it for the department, but not the other applications. And some average presence we have in the field of design for laser additive manufacturing, modeling and simulations, and application development, because we are doing it for the nuclear fine, but there are many other avenues where it can be tried out. So what we are focusing on here, if really we want to be self-sustained in this technology, we need to have expertise into all the 9 domains, not 1 or 2. And I'm counting a lot on the collaboration with various institutes for this. For example, modeling and simulations, and then design for LAM. All academic institutes are working with us. Again, and we are trying to work with the people who are developing materials so that material feedstock can be tried out. I'm also trying to have a some alliance with the Defense Institute, where the space organizations, where we have quality control and assurance in trouble. So all these things can be tried out and make into this. But idea here is, as far as I'm concerned, or the lab what we have is concerned, think of developing whole expertise into all 9 domains is not possible. This is only possible with the collaboration with the different institutes, and where in such a gathering, when I'm talking about and pushing this, so that if you have some novel idea and try to have some idea to work into the domain where we have yellow and then brown areas, then we are happy to support and work on this. Now, when we talk of the challenges, what we have is the technology is new, and there is a decent lead at the international level. We are gearing up in India. We have done really pretty well if we talk of developing these machines and modeling for our nuclear energy application program. But there are many challenges still. For example, when you talk of the materials, the refractory metals and the ceramics for LAM is again a big issue, and which need to be worked on, make the things aware. Then again, another issue is, the people have very limited awareness. Skilled manpower is not there. Expertise again, in very small niche area. Material data properties, yes, is a big challenge. Again, there is a issue with the process qualification, because you guys, if you go to some industry and say that they say whether you are able to do it, what is the certification, what is the quality. Still, the standards are coming, in the international market. And for example, STM trying to make some of the standards and regulations on this, but again, there are problems. For example, if you want to go for aerospace industries, or defense industry, or you want to work on this, there is also not clarity about the regulations and the licensing procedures. So, which is also a challenge in how to adopt this. These are, but nevertheless, we have to work on these areas to strengthen the field. And again, we have to go for the manufacturing of the commercial products so that it can be economically viable to move ahead with this. We are doing a lot of thing into this. Awareness is really going, and then we all have to work, leave our comfort zone, and therefore, whenever I get opportunity to speak to the people, specifically when I received the invitation from the institute, your institutes, to give it a FDP, I thought of just doing it. Really, thing can be done. We need to work on national skill development program for additive manufacturing so that it becomes this knowledge and technology sharing mechanism for the faster commercialization. One of the issues that we have to work on. Optimization of the nuclear components, we are working on it. And then third thing is specific manufacturing technology and equipments for nuclear applications. We are thinking on and working in this area. Definitely, a lot of things are required in terms of the material and material data development. And now today we are talking of a lot of artificial intelligence and machine learning. So feedback system has to be come up because today machines are operating in the open loop, and to certain way it is a closed loop. But again, AI and ML has to be brought in so the machine can be more attractive, faster, and smart enough to take care of the process instability which is generated during the process. So what will I conclude with this is yes, there is lot some effort in the niches development, and the results are yielding. We have incubated the DD technologies, and PPF is also coming up. LAMP services we are providing for LAMP DD and the PPF on chargeable services. And for academic institutes, if they come up with their own powder and ask us a suitable uh, time slots, normally we don't charge from them, but again, issuers, the scholar has to come with the powders, stay with us, and then get the time. And these are possibles. And again, slowly it will be more available, and we are trying to cater the needs. That is the reason we have now 32 institutes collaborating with us in this. What I want to emphasize on is that innovation is required not only into the process development and material characterization. We need to go ahead of it, because a lot of things, what normal scholar thinks when they do the PhD, they think that they want 3 or 4 journal paper published so that their PhD is done. But if you talk of in longer run, you may have PhD, but after that what? And which is the important point that we need to think on, consider. So we need to have innovation holistically. We need to develop some processes specifically for the engineering companies, not making the bulk and characterizing and talking about that. So really apply it where it can be applied. We have to done. Collaborative incubation, we are inviting in various material identification domain, specifically in powder atomization, pre-processing and post-processing development, so that we can make this to technology to the next level. And what I am talking of is we all should contribute in the best possible way. And I invite you all to access the opportunity, encash it, and join the mission of additive manufacturing in the India, so that really the country can be a giant in this area. A lot of good things are happening in the country, but again, it's a time for us to take a leap and go to the next level. Which I stop. Thank you very much for patient listening. If there is any question, I'll be happy to answer you.
Thank you, Professor. Thank you for your wonderful presentation. So far, we have only considered about producing the part. Now we can able to learn from how the machine is produced. There are some questions from the participants. I'll list one by one, Professor. You can so that you can answer. Ritvik, one of the participant asked, can we predict the properties of the material before printing?
Yeah, it is doable. And see, what you have to understand, normally when you talk of the material property, it is in the range. It's never the single value. We all know that. And in principle, what we have to think on those lines, if you're printing only single material, so if you see the process level, there would be a high cooling rate. So there would be very fine microstructure developed. And on the other side, we'll have the whole process, which will be towards the casting. So, if I say laser additive manufacturing is nothing but a rapid casting, that is the word you can think of the process point of view. I'm not talking of the, pre-processing part, other things. So if you join this, then the microstructures can become up. So what will be eventually happen is the material property will be more towards the wrought material, but it will be lesser than that. And in some of the specific cases, it can be better than if you are able to generate mixed microstructure. So what I want to say is definitely it can be predicted. Properties can be predicted. I can say that if you want to go with the thumb rule saying what will be the property, at least you can qualify with the it will be always better than the cast material. So that is the one part. And on the higher side, we can definitely work on it, and the making can be done. That is the answer I have.
Yes. One more question from Mayalagan. How the process parameters for different materials will be selected in our machine, in our developed machines?
See, what we do is we have a comprehensive plan, and specifically these are done by the people who are developing the process. That we two ways of doing it. Number one is if the people have already done with the something similar alloys. For example, they had a nickel, and then we have done a lot of nickel alloys. So the property comes from the nickel close to that. That is one part of it, which is derived from it. Second point is whenever we are doing something very different material, then what we do is we go for a Takuchi technique. We lay some 9 tracks, 9 arrays, then understand the things and then come up with the optimum parameter. So there is a defined scientific way to start with the new material, which is not in the database, right? Because we also try to have some modeling part of it, is specifically deriving from the first principle. But our experience is that many of the parameters are not available for many alloys, in the open literature. So that limits our requirement. But therefore, no, if something is very close is known, you can use these data as input and derive the parameter for the next level. So that we do, and it's a regular. Therefore, people are able to go to the optimum parameter in a 2 to 3 years, which is not possible otherwise.
Yes, and next one from Dr. Ravi Bhatt. Can we deploy LAM for metal matrix composite? If so, then please suggest some current research domains, Ravi Bhatt. LAM for metal matrix composite.
For example, you saw that metal matrix, you saw one example I gave you about the tungsten carbide. So making the component of the tungsten carbide, specifically with the cobalt matrix is one of the things that we are doing. And I have, if you see my literature, the research paper, one of the most cited paper, just go to the Google Scholar, type CP, go to the Google and type C.P.Paul, and you'll see my Google Scholar link, and there you find it. One of the most cited paper is we have tungsten carbide 12 cobalt with the MMX, and I did long back, maybe somewhere in 2006 and 7. This paper is published. So really, it's possible, and material is not a big deal, and only But see, this is very interesting. I'll just share here. You have two species here. One is tungsten carbide, another is cobalt. And if you talk of the absorption of laser beam, especially near 1 micron, is more in tungsten carbide than the cobalt. And you want to melt cobalt, not the tungsten carbide. You want to make a matrix.
Yes.
So again, you have to come up with some strategy, how to play so that you are not melting the tungsten carbide. Though advantage is because tungsten carbide has got really high melting point as compared to the cobalt. So what should be your process parameter so that you are able to, some way play with this and make the things to be different. Now we did it, and this is really available. So as far as the topics are concerned, making the silicon carbide into the SS, then UMM carbides, then ferrous boride. These are the topics where people are thinking to build. A lot of requirements are there, and for sure in our group, if we talk of, we do not have enough manpower to cater all. So some of the scholars take up this assignment and come with the metal powders. We'll be happy to extend the facility to them, and if it is for the purely academic purpose, no money will be charged, and things can be taken to the next level. Yeah, it's possible.
Yeah, one more question from Varsha. Why one should use laser over WAM, WAM, wire arc additive manufacturing?
Varsha, I'll say this. If you see some of the figure, for example, maybe for example, impaler, maybe I'll just go to the slide back so that. For example, this component. Here the thickness is 0.5 millimeter. Not possible with the WAM.
Okay.
Similarly, another component I'll show you. The compressor blade you are seeing here at the bottom. The curve with the 0.5 and 0.45 thickness. Not possible with the WAM. Then, so there are applications, but I'm not saying that WAM is bad or good, but important is we need to select the right tool for the right application. Suppose you want to have a bulk deposition, large components. There probably laser at these manufacturing systems may not hit this, but again, WAM can lead. But if you want to have very fine features, small things, control heat deposition, because in the VAM, whatever you say, you cannot achieve the thermal gradient that we achieve normally with laser additive manufacturing. So this makes the whole scenario different. So I think I answered Varsha's query. Yeah.
One more question from the same speaker, same participant. Does different infill patterns affect the microstructure even the infill density is 100%?
Yes, different infill pattern changes the microstructures. And again, it's the open secret now. People normally use 67-degree rotated layers to build strong microstructures and strong 100%, nearly 100% test structure. So these are the part of the game, and once we start working on it, we learn many tricks, and then there is always a question: if 67, then why 67? And why should use only 67? So in one of our journal paper, we have already answered these questions, and so things are there, and sticks are already played. And see, at the end of the day, I will say one line: laser additive manufacturing process development, though it looks scientific, but still it's art because people are learning. Once it is learned and then push it to the textbook. And now, if you talk of the CNC machines, the guy who goes and put that program and start and it prints, it makes it manufactures. And that was just grew in with some 50 years time. Something similar. Maybe in next 10 years, things will be on that level, and things will change. Yes.
Yeah. One more question, Professor. How you measure the laser spot diameter in case of coaxial nozzle with multiple lasers?
In general, we don't use multiple lasers. We use only single laser because in one of the applications we tried. But what you have to do is in all the cases, whenever it comes to measure the spot diameter, the standard procedures to measure the burn spot. So you will have a material, you will give a spot, and that is the way it is measured. And it is the same some time predefined. For example, we keep it 100 millisecond, so we switch on the laser for 100 millisecond, give the power and see what is the spot coming, and that is the way it is defined. So we write in our project that the spot is measured using this method, so it becomes transparent. So that is the way it is done. So it's not only with a single but even the multiple, this can be done. And in multiple laser, if you're using to melt a material, the alignment becomes critical. Because what happens now, if you talk of in general with the lasers, as the power goes up, the beam diameter grows a bit, and if you do not align it perfectly at the low power, as the beam grows, it's filled all around in the um, fiber, and then it comes out to, then it becomes misaligned. For example, if you're using three lasers, then in spite of having a circle, you'll have a something close to sphere. We'll have three
Yes.
circles. Yeah, so that sort of thing happens. So one has to be careful, and this becomes challenging when you are using for omnidirectionality. You are making some circle or something, then width will be changing, and this is the thing. So again, it's a thing. If you align it properly, give a shot for the 100 millisecond, measure it, and see how the melt spool has come over, and based on that we can decide on it. Yes.
Sir, I have some question. If you purchase the machine from foreign peoples, they will supply the raw materials. In case of yeah, can you hear me, Professor? Yeah, if you purchase the
Yeah,
machine from foreign players, they will supply the material. What about our inbuilt machines, Professor? The raw material like powder or wire, will you supply or we can?
See, I'm working on this projects, because presently we are counting on external sources, and many materials which what we are using are standard material which are used for plasma torch, plasma deposition. That is one thing. Now India is having this ecosystem evolving. So now I can list at least three companies who are able to supply these metal powders in the country. Again, today the quantity they are asking is a bit more. They are not saying is applying. So they will take a very long time if you ask for a 5 kg or 3 kg, But again, you can get it with a lot of persuasion. That is there. But again, if you want to have a quantity, maybe the 50 kg or 100 kg, it can be done. You can negotiate with them at that faster. That is one thing. I have a vision to have a some machine built which can give maybe 3 to 5 kg per day. So you can, for the research purpose, we can try different composition. Today we built some 3 kg powder made, and then tomorrow it's did some slight tweaking of the composition, build that. So that is the plan, and that will be ideal for all our academic requirements. So today we are not doing it. We are counting on the external this, but again we have a plan to go ahead and let's see how the things evolve and how the fundings and other thing comes to us, and accordingly we'll do that.
One last question, Professor. A few of the participants also asked the same. What is the procedure to use 3D printing facility in RRCAT? I also want to extend the question. Can you brief about the National Skill Development Program which you have stated in your presentation, Professor?
What is the the later part of the question?
National Skill Development Program in AM.
Yes, National Skill Development Program, I'm talking of it. So we have now AIC Pi Hub that we have already started one incubation center, which is one of the vertical working on advanced training and certification courses on this part. Regularly, with some time gap, we are offering some courses. And our whole idea is specifically in the niche areas, there can be initial course on theory of that, which can be done online. And after that, the student can come to us, spend 2 weeks with us, and get some hands-on the machines. So they have really good effect about it. So at the end of the day, now as the industry matures, there will be a lot of opportunities. So in the last, if I see 2016 onwards, we have PG students passing out from our institutes, with our collaborative institutes and all are getting very good placement, either in India or abroad. Few became
yesterday also we have Jinoop sir also.
Yes, Jinoop is my one of the students,
yes,
and it's the. So what I'm saying is, since we started focusing not only on the just pushing the things, but pushing to the level where things can be brought to the level where information sharing can be done and made. So this is the really good program, National Skill Development Program. You can just part it, and we are not charging a lot of money, because the idea is not to make money. We know that the scholars don't have money, but again, some minimum money we have to charge so that the expenditures can be met. At least whatever that we are spending at here at RRCAT. So that can be done. And again, if you bring the powders, we can extend the free printing of the material, so that your research can be supported and you can come with some novel idea, so that no one has it should not happen that you could not do this because you never had the opportunity to have access to these machines. So this should not happen. So we are trying to do that, and that is a part of the National Skill Program. Yeah.
So as a teacher, we can also apply for that National Skill Development Program, Professor?
Yes, whenever there is announcement, you can apply for it. As a teacher, you can apply. And again, I'll say that once you have that skill development program in your hand, you can think of getting some funding specifically in your area to have a small machine, specifically the machine that I'm thinking of, to come about 45 to 50 lakhs. Not very costly as compared to this.
Okay.
And start solving some of the local problems and coming up to this. So this is a really good initiative can be, and make the things to the big level. That is my plan. Yes.
Thank you, Professor. Thank you. So now I would like to extend my heartfelt thanks to Professor C.P. Paul for readily accepting our invitation. Yeah. Is there any questions?
Sir, yes, sir. I have one question too, sir.
Yeah. One last question, Professor.
Good evening, sir. Hello.
Yeah, good evening.
Sir, I'm from Jadavpur University, Kolkata. So, yes, sir. I want to ask one question that I have a plan to make one metal matrix composite with help of by adding some carbon allotropes by using additive manufacturing. Is it, sir, possible to make in powder bed fusion in your lab or something? Because here the machine is not there, so that is one problem. I'm a research scholar.
On the spot, I can say machine can be extended. You come with the material. Before coming and before putting the material, discuss with us what should be the specification of the material so that you don't buy wrong material. It can be done. And again, it's a game that our people do the magic in the lab. Whether it will come or not, so that will be decided based on that. So, but again, it is doable, and definitely I welcome you to our lab to work on these areas. Before coming there, please do write to me, and very simple. My email ID is paulcp@rrcat.gov.in. You can write to us. Definitely, our people will answer, and we'll pick up. You have to, as a scholars, you need to write a short proposal, and it should come through your supervisor, not yourself. So that there is forum, and then the material we can extend the facility. Not a big deal. Yeah, it can be tried out.
Okay, sir. Thank you, sir.
Thank
I
you.
will connect.
If there are no questions, we'll end the session.
Sir, I have one more question.
Yes.
Paul sir, when you have developed the indigenous machines, how did you manage the digital workflow of AM? Which software you have used?
See, presently we are using both the technologies, DED as well as powder bed fusion. The first version we developed was, I'll just tell you how things evolved and what we are doing today. In the first machine, what we did is we had a mold and cavity module of UG, Unigraphics. So suppose whatever we wanted to make, we used to make, the negative part of it and then convert it into this, get it sliced, generate the tool path, in the linear way. And we used to have a small code running to change the z-axis, because if you make a tool path for material removal, it will always be from top to bottom. And if you want to make it, it will be bottom to top. So that we did in the initial phase, when we started in 2003. Some of the complex structures came in this, and the thing can be made and a success. But with the time, and we have now commercial softwares available. UG has got now AM module. Similarly, you have Mastercam has got A plus module, which is again AM module. So we are directly using these modules now in our machines, and all these things evolve with the time. It's not like it happened overnight, but initially we started with this. This is for DED. And for powder bed fusions, presently we are using software from Materialize, Belgium. So, and it's a costly one. I will not, and we are talking to the people to have a low cost version of it. Specifically the smart people in the country. And again, we have some program to build these softwares here so that the price should be attractive enough for you guys so that these can be built. But again, as far as the making simple structures like block, other things are converged, it can be written manually also. It's not a very big deal to do such programming. Specifically, once you have interface with the MATLAB or C++ or other options available besides, these can be done directly. But for the complex geometry, yes, you need to work on. And what I want to emphasize on here is for making or building many companies, it's more of the taming strategy. Even if you have a very good software, the software can show and you can have a quick vision in what will be done. But again, the person, who is sitting in front of the screen decides the whole topology and makes the thing into different game. So that we do, and that makes the things into different aspect. I think
yes, sir, thank you.
Hope I answered you, Deepak.
Yeah, yes, sir.
Yes. Thank you, Professor. Our heartfelt thanks to you for readily accepting our invitation and delivering an insightful session in your busy schedule. Your contribution was invaluable, and the participants came to know about the machines too. We wholeheartedly thanking you, sir. I also want to thank our management and participants for their support. Thank you, Professor. Thank you.
Thank you very much.
Thank you.
Thank you. Right.